moving into 7.3 today, and we have been talking about exponential functions. We've seen how we can represent growth and decay, connecting to real-world stories. We've seen how we can graph exponential functions. Today we're going in a little different direction, and we're going to be looking at the inverse of an exponential function. And so the context for our story today is about duckweed. If you haven't heard of it, this is a type of plant that multiplies fast, and it grows on the surface of a pond. And so if you think about like a lily pad growth, that's kind of the type of plant that this is. It multiplies very fast. In fact, the number doubles every day. And so a pond that has this type of plant on it, it can get completely covered in a very short time. And that makes the surface kind of look like green grass. And so the area today is going to be measured in square meters. The area of the pond that is covered by the duckweed. And it's going to be a function of time. And so beginning with 1 square meter of plants on day 0, after 1 day, there's going to be 2 square meters of the plants. After 2 days, it's going to go to 4 square meters. After 3 days, it's going to go to 8 square meters, and so on. So every day forward will result in the area doubling. And so that's an exponential process. It fits our characteristic of exponential patterns where we're continuing to multiply by the same number. And so the formula that is going to describe this process is A equals 2 to the power of T. So A, the output, is representing the area in square meters, and then T, the input here, represents the time in days. And the graph that we see down here below is showing this process for the first 4 days. So you're going to begin here by using this graph to answer the 6 questions that you see off to the side. All right, so we're going to come back together here and check in on these first 6 questions. So first off, Max, what did you say? What is the input for this function?
Y.
So we're going to be either choosing between area and time. So thinking about those as our 2 variables. And so we have our graph here, so we can look at how it's labeled on the axes, but we can also look at the equation here, like what position would we like input a number in? The time, yeah. So the input here is going to be the time, and that's being measured here in days. And so we can see that in our equation. So the input is going to go in this position here. Input is labeled on the x-axis. So if we're inputting time in here, that would be like if we knew a certain number of days that this has been growing, we put that number of days into our function, and then it's going to output the area that it is covered. And so area we see here, our output, is labeled here on the y-axis. Okay, so if we take a look then at the next few questions, this is now asking us a question about the area. So it's given us a certain size of the pond that is covered. We are thinking about kind of working backwards and figuring out how many days did it take to get to that. So let's look at the size of 3 meters squared. If we take a look here at the way that our area axis is labeled, so 3 square meters is going to be right here between 2 and 4. And so let's think about drawing a line straight across. We're going to connect that with where our curve is. And then let's go straight down to the time axis, and we'll see how many days this is. Now, notice on the time axis, each little square, it looks like there's 5 little squares for every 1 day. So each little square is like 1/5 of a day. So it's somewhere between 1 and 2 days. It actually looks like it's 3/5 of the way. If we were to turn that into a decimal, we could say that it would be 1.6 days. So then if this grows to a size of 6 square meters, let's start here with an area of 6. We're going to go over here to our graph. We'll go straight down, and that should be 2.6 days. And then an area of 12 square meters. We're going to do the same thing here. We'll bring this line straight down, and we see that that should be 3.6 days. So can any of you tell us here now, without the help of the graph, because this next question is not on the graph, how many days would it be to get to 24 square meters? Anything you notice here? Go ahead, Anna. 4.6 days. Why?
Because for all the other ones, like 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24.
Beautiful. So we see this pattern in these areas. We see every question is the doubled area from the previous area. And we can see here from our graph is that every time our area doubled, the amount of time added 1 day. All right, so we're going to take that down to these tables. And so if we think about the area doubling, every time we add 1 day, let's go ahead and fill in all of the missing empty cells in part 7, and when you have those filled in, I want you to also answer part 8. So you're here going to explain in words like how were you able to fill in the missing values in the table. All right, so we're going to take a look together here at our first table. So we have our areas filled in, starting in an area of 1 square meter when we were told back in the story that that was at 0 days. Notice how all of our areas are doubling. And we're seeing it again here in the table. So every time the area doubles, the time in days is going to add 1 day. So we're just going to continue to add 1 day to get all the way up to like an area of 32 after 5 days. If we take a look at the second table, this actually matches that first set of questions that we did on our graph. So we saw that when the area was 3, that was 1.6 days. When it doubles, it still adds a day. So we get 2.6 days, 3.6 days, 4.6 days. Now we could continue doubling our area on the top and adding 1 day on the bottom to help us get our table all the way filled out. All right, so now we're going to take a look at the bottom table. So it's giving us a value kind of in between to start with. So it's telling us here that to get to an area of 5 square meters, it takes 2.3 days. We could actually verify that going back to our graph. We didn't look at this one earlier, but if we were to go ahead and find an area of 5, do that in that red line here, and I'll go ahead and find the position on the curve. Straight down. Actually, that one was, it's like in between 2.2 and 2.4. So that's how we end up getting the 2.3. And so we can use that number of days to help us in moving forward and even going 1 step backwards. So as the area doubles, we're going to continue to add 1 day. And then let's think about going backwards. So if the area was at 5 square meters, well, that would mean that that duckweed plant would have had to have started growing before this particular moment in time. And so if we think about going backwards, it's actually dividing by 2. And what should happen with the number of days? What do we do with that, Remy? Subtract a day. Yeah, so when the area was 2.5, then we should be at 1.3 days. So doubling forward adds a day forward. Halving backward subtracts a day, or it takes us 1 day back. And so to summarize that, for how we were able to fill the missing values into our table, I'm guessing you said something like this. I'm going to say here every time the area doubles, you see that the time adds 1 day. And to think about that last situation that we talked about here on the red table, we could even extend this and make a little note here that if the area halves, well, then the time subtracts 1 day. All right, so moving on to the next side of our paper, we already talked about the input and the output for what we're going to think of this as being the original function. So actually, off to the side here, I'm going to make a little note. Our function that we started with at the beginning of today was a equals 2 to the power of t, and we saw that our input was time in days. So we could plug in a number of days, and it would output an area. So that was the output. Okay, so transitioning now to start to think about the inverse, I'm going to have you go ahead and answer questions 9 and 10. So you're going to be thinking about what would the input be for the inverse of this function, and what would the output be? All right, Simone, what did you say for the input of the inverse?
Area.
Okay, great. So area used to be the output. When we take an inverse, we know that the input and the outputs are just going to switch. So the inverse function is going to be one where we can now input the area, like how much of the pond is covered, and then it should output the time in days. And that's kind of what is shown to us here in these tables. We're going to look at some tables that are extended out all the way up to an area of 26 square meters. And it has the decimals for the time and days just a little bit more accurate. So it has this out to 2 decimal places. So looking at our table here, we have an input of area that's outputting an amount of time. And so without yet knowing a specific formula and equation for the inverse, we can still show and describe the inverse relationship with the tables. Let's look at some that we've already worked at so far today. The very first one that we looked for on our graph is when is it going to have an area of 3 square meters? And we actually estimated it to be 1.6 days. A little bit more accurate is actually 1.58 days, but that's pretty close to what we got of 1.6. All right, so notice how it's getting us all the way up to an area of 26. So to help us think about this inverse relationship between time and area, we're going to take a look at some notation. So we're going to use this notation here, t of 24, and as a sentence, what that represents, bless you, is the time it takes the duckweed to grow to 24 square meters. Using that same type of language, I want you to write on your paper, what is the meaning of t of 8? Okay, great. And I'm actually going to have us add one more little piece in. So I know this piece was also missing from my example up here, but in parentheses, I want you to add in when doubling. So we're just making note of what our growth factor is. All right, now instead of using t of 8, to represent this inverse relationship, or t of any number, we're actually going to use a new notation here. So a different way to represent the exact same thing, we're going to start with t of 8. This is going to turn into log, so I'm writing out the word log, L-O-G, and this log, I want it to have a base of a little 2. So I'm going to make a 2 that's not a regular size 2. It's going to be small. It's kind of down here below. We call that a subscript. And then I'm going to put another number that is a normal sized number. That's where the 8 is going to go. So we're going to make the 8 the same size that you did the L and the O and the G. Log is short for logarithm. So this is the full name for the inverse function, but we're just going to shorten it and call it log. So when we look at this phrase here, it means exactly the same thing as T of 8. It means the time it takes to grow to a size of 8. And then notice how the little 2 down here is telling us when doubling. So this is what it's continually being multiplied by. Now, we could actually look back at the table and evaluate this. We can figure out what this is equal to. We can figure out the time it takes to grow to a size of 8 when doubling by looking at the area of 8 and looking down below and seeing that it is equal to 3 days. All right, so let's make note of a few things here in this statement. So notice how the answer, the output, is time in days. Notice how the input right here was the area. And then notice the position of the little 2 down there. That was our growth factor. So we know this is the inverse because we can see that the meaning of the input and the output have switched. One more little thing that I'm going to have us write off to the side here is just specifically how do we say this left-hand side aloud. So off to the side here, I'm going to put some quotes here because this is how we say it. We're going to write log base 2 of 8. So these words here that I've underlined will help you to correctly and confidently say this. So we don't want to say log 2, 8. That would be confusing to say. We're going to describe the little number down there as the base, and then it's of whatever that bigger number is. All right, so now that we know that there is an inverse function, we know how we can write this out symbolically with a log notation. We're going to take a quick look at the inverse graph. So we're going to see how the graph of the original relates and compares to the graph of the log. All right, so I'm going to do a little bit more labeling here. So I'm going to call this first graph the original. And this is what we looked at the very beginning today. So that's A equals 2 to the T. The input is time and days. And then let's go ahead and label this one here as the inverse. And we saw that it was log base 2 of 8. Well, 8 represented an area. So let's just put an A in that position to generalize. It's the area that goes there. And instead of saying that it's equal to time and days at the end, I'm going to actually put the equal sign in the front. And I'm going to use a little T here to represent that the time and days is now the output, and the input is the area. So a couple of things here on our graph. So notice how on the original graph, the input is labeled here on the x-axis. That's time labeled on the x. Well, when we switch over to the inverse, notice how now time is labeled on the y. We've seen that before. That's just what we would expect. The area that used to be labeled on the original y-axis is now labeled on the inverse x-axis. So the axis labels have switched. Let's take a look at what's going on with the actual ordered pairs on the graph. So if we look at the original one, I'm just going to highlight a couple of points here. So we have the point 0, 1, which means after 0 days, the area is 1 square meter. Well, we can actually represent that same information on the inverse graph. That point would be right here at the point 1, 0. When it is at an area of 1, it has been 0 days. Same information, we're just saying the sentence in opposite order. Going back here to the original, after 1 day, the area is 2. When we go here to the inverse, when it's an area of 2, it has been 1 day. All right, let's do one more. On the original graph, when it's been 2 days, the area is 4. And on the inverse graph, when the area is 4, it has been 2 days. So the information is really the same. But what's happening to the x and the y ordered pairs? What do you notice? From the first graph to the second graph, what happened? Ernie?
They like were inverse, so they would switch the x and the y.
Exactly. Just like what we saw before with inverse graphs, we see the x and the y switch. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 2, 4 becomes 4, 2. And that should continue all the way through if we were to look at more points on our graph. All right, so let's just make some notes here for how our graphs are related. So one observation at the start was that our axes are switched, so the way that they are labeled. We saw that the xy ordered pairs switch. But the important piece here is to see that it's really the exact same information represented on both. All right, so in this next section here, so we're going to revisit those time and area tables that we looked at on the other side, and we're going to use that to help us evaluate some more logarithms. And so if we take a look here at part A, the first one is asking for is log base 2 of 1. And for each of these, we can just think about, like, what does this represent in the story? So this is asking, how long does it take, how many days does it take to grow to a size of 1? Well, we can answer that here in our table. So if we look at an area of 1, we can see that the time it took to get there, sounds weird, was 0 days. If we look at the next one here, log base 2 of 4, this is asking, how long does it take to grow to a size of 4? We're going to find an area of 4 in our table, and we can see that that took 2 days. One more together here, log base 2 of 8 is asking, how long does it take to grow to a size of 8? And we see down here that that is 3 days. All right, so I want you to continue filling in the rest of these and challenge yourself to find the values that are not given in the table. So for example, the very next one, the time it takes to grow to a size of 32, this isn't in the table. The table only goes up to a size of 26. But think about what's happening here with the ones we've answered so far and how you still might be able to figure out that result. When you are done with number 13 here, I want you to actually continue with number 14. All right, so let's come back together here. So I just filled in the answers that we could have gotten from just looking at our table. And we're going to talk a little bit about how can we evaluate these logs, how can we get these answers in this last column. So if we go back up here to the top row and look at what's happening in these two answers here in the middle. So we were going to a size 4, and then it's going up to a size of 8 in the next question. So we see here that our area doubled, and when that happened, we added 1 day. So if that area were to double again, if 8 doubles, it actually gets us to an area of 16, which we're not being asked a question about that, but it's kind of an in-between value that we need to get to the last one. Because if you double 16, that's how we get up to 32. So because we doubled twice, we actually have to add 2 days instead of just 1 day. So it's kind of like we just skipped over the answer of 4 days, and that would have been an area of 16. We're going straight to the answer of 5 days that's corresponding with an area of 32. And we have a really similar thing happening when we take a look here at the second row. So in the second row here, like to go from an area of 5 to 10, it doubles. So on the bottom here, we add 1 day to get from 2.32 to 3.32. Now to get from 10 to 40, it doubles twice. So 10 times 2 is 20, and then 20 times 2 is 40. Because it's doubling 2 times, we're going to add 2 days, and that gets us up to 5.32 days. And it's kind of the same thing on the bottom again. So if you think about going from an area of 6 to 12, it doubles. We add 1 day down here. 12 times 2 is 24, and then 24 times 2 is 48. So doubling twice adds 2 days to get a final answer here of 5.58 days. All right, now number 14 here is asking us about this little piece here that we evaluated just a few minutes ago. We found that log base 2 of 2 equals 1, and we wanted to explain like what this means in the duckweed context. We want to put this into words. Mark, how can you do that?
I said it takes 1 day for the duckweed to grow to an area of 2 meters squared.
Awesome. And I want to write down here below a slight variation of this that would be a different way of saying the same thing. The time it takes to grow to an area of 2 meters squared is equal to 1 day. And so the big thing we want to see here is just that this log expression here, like that left-hand side, that represents a time period. The output is time, the input is the area that we're putting in. So now we have a different type of statement here in the next part that we want to do the same thing. So we want to interpret that. We're going to explain what this next equation means in the duckweed context. And so I'm going to break this into 4 pieces. And so the first piece here, I'm just going to put a box around this in blue, is just that little part there at the beginning, log base 2 of 3. And so to help the interpretation of the beginning of this, we know that log represents a time period. So let's describe that log base 2 of 3, even though we haven't evaluated that part specifically. What it represents here is the time it takes to grow to 3 square meters. And technically, I'm just going to add this in parentheses, this is when doubling. So remember that little base number down there, because it's a little 2 down at the bottom, that's just telling us that our growth factor is 2. All right, now let's move on to the next part of this statement. So the next piece I'm going to circle here is that plus 1. So if the first part here in blue represents a time period in days, then when we add 1, the 1 should also represent a time period in days. It just represents 1 day. So let's add that here to our sentence. The time it takes to grow to a size of 3 plus 1 day. So just adding 1. And then it is an equation, so we have an equal sign here. So I'm just going to write that this is equal to, or you can write is the same as, and then we're going to put into words this little piece on the other side. Log base 2 of 6, which means the time it takes to grow to 6 square meters. So when we go to the back, when we go back to the start of this sentence, if we were to read the whole thing through, does this make sense that the time it takes to grow to a size of 3 plus 1 day is equal to the time it takes to grow to a size of 6? Would that be correct? Yeah, it should, because we know every day forward means that the area is going to double. So if we add 1 day, that area should multiply by 2, which is exactly what's happening here in this statement. All right, so let's take a look here at our final section here. So we've got our quick notes box. We're going to connect this back to our learning targets for today. So first off, we wanted to see how the input and the output of a logarithm describe an exponential relationship, and also rewriting exponential equations as log equations, and vice versa. So in the first piece here, let's actually just divide this into 2 sections. Let's say here that log is the inverse of an exponential function. All right, and the example that we saw from the duck-weed problem today is we have the exponential function a equals 2 to the power of t, and then we saw the inverse was log base 2 of a equals t. And in various ways today, we just saw that the input and output switch. All right, and then our other learning target here was about evaluating logs. So we did a little bit of this with those tables. So if we go back here and look at the tables, we were evaluating logs when we figured out that log base 2 of 4 was equal to 2. We're just figuring out what is the answer part, what is the output of the log part. And it turns out that we don't always have to do this with a table in front of us. In fact, we might not have access to a table. And so I want to share another way that we can think about this. So instead of using a and t, I'm going to generalize this a little more and say that we have log of some little base down here that we're going to call b, of another number that we're going to call y. And evaluating means that we're trying to figure out what this is equal to. And so here's how we can answer that question. We're going to think about b raised to what power equals y. And so here's a little example of one that we're already familiar with from today's story. We saw that log base 2 of 8, the time it takes to grow to a size of 8 when doubling, we saw that that was equal to 3 days. Well, let's look at what's happening with the numbers. If you start with the base of 2 down here, and you raise that up to the power of 3, the answer is going to be 8. So in the little corner here, let's just make a little note that a related statement to this, the exact exponential form of what that log question is asking, is 2 raised up to the power of 3 is 8. And so notice how the answer to a log is the number bits in the position of the exponent. In fact, that little red line that I drew here, I like to think of this as the log loop, meaning we're starting with a little base, we're going to loop it around the number on the outside, 2 raised up to that number should equal the 8, or whatever number is in that position. All right, so we're going to take just maybe about 4 minutes here to work through the check for understanding problem. All right, so we just have a couple of minutes left here, so those of you all that are done, I just wanted to display this here so you can get a little bit of feedback and check off your work. When we get to the second part here, so the evaluating the actual answer that we're looking for is what I have here in purple. What I wrote in red, that is just a statement that's related to the question that was being asked, but also helps to explain, like, how did I get that answer? So, like, log base 2 of 8 is 3 because 2 to the third is 8. One on here that was kind of interesting is the square root symbol. So remember that anything raised up to the power of 1/2 is going to be represented as a square root. So that was one that was interesting. Also, anything raised to the power of 0 equals 1. Those are a couple other ones to point out. At the very end here, notice that we actually cannot do the log of a negative number. And with the duckweed story today, like, that makes sense because you can't have a negative area. And if you try to think about it the other way, like 6, you can't do 6 raised up to something and get a negative number for your answer.